Topic number 5, put down as practical consideration. So here in this topic, we're going to look at 3 subtopics. One of them is called static hazards, and then noise margin, and the last one, fan out. These are some of the things you need to consider in practice. So when you're dealing with real practical circuits. Start off with static hazards. Propagation delay. So in practice, the output will not happen instantaneously when the input changes. For example, if I change the state of the input from low to high or high to low, the output doesn't react instantly. It takes some time for this to occur. So the signals take time to travel from inputs to outputs, and this is known as propagation delay. So there's a slight delay from the changes in the input to the reaction at the output. So consider an inverter. So I have my inverter here. So if I change the input from 0 to 1, so 0 to 1, the output doesn't change instantaneously at the same time, but the output will only react sometimes later. And this time delay here is what we call the propagation delay. So the time taken for the signals to go from high to low at the output when the input changes from low to high in our inverter. And to measure this time delay, we need some form of reference in order to measure when the input change and when the output react. So in this case here, we use the 50% of the rise time as the reference. So backtrack a bit. Previously, when we talked about ideal signals and ideal components, we use rectangular pulse that do like that. So in this case here, we see that the rise time happen instantaneously as well. So if we want to change from 0 to 1, at this instance, we go from 0 to high in no time, meaning that there's no delay. But in practice, the signal takes time to rise from 0 to whatever value that is, let's say 5 watts. From 0 watt to 5 watts, it takes time for it to rise. Call this the rise time of a pulse. So in order to measure when a reference between the inputs to the outputs, we take a reference point. So in this case here, we take 50% of the rise time as the reference. And here it will be the 50% of the pulse going from high to low, so that we can measure the time delay between the two. So there are 2 times to consider here. So one is the delay for the outputs going from high to low. We call that the TPHL. And then there is the other one for the outputs going from low to high, which is the time TPLH. So P is the propagation delay, L is low, and H is high. So normally, these two times is the same for most components, but once in a while, you probably find some components that have a different time for going high to low compared to from going high to low. Okay, so this is the practical consideration. That's how real device react and how real signals behave. Signal doesn't go from 0 to high instantaneously. It takes time for it to go from 0 to high. And from inputs to the output, it also takes time for the components to react. Or it takes time for the signals to travel from the inputs to the output. So static hazard is a hazard that results in this propagation delay of the signals. So this is what we have looked at so far in ideal scenario. So we see that we always talk about if the input change from 0 to 1, then the outputs will go from 1 to 0 at the same time. So this happens instantaneously, and this is ideal case. And in practical circuit, as we mentioned just now, it will take time for the signals to propagate through the gate. So from the input to the output, it will take some time for the signals to come up at the other end. So here I put down a note here for simple illustrations. We're going to use an ideal pulse so that you can see much clearer of the effect of the propagation delay. So I'm using ideal rectangular pulse rather than using a pulse with a rise time, so that this is easier to illustrate. Okay, so in practice, this is what happens. So if the input change from 0 to 1, the outputs only go from 1 to 0 a short time later. So it takes time for the inverter to react. So you can see that if you have many stages of logic circuits, so this delay going from the inputs to the outputs will propagate. So for example, if I have one inverter, or if I put many inverter, okay, although they're doing the same thing, so I put 3 inverter, I end up with the same thing, but here we have 3 times time delay compared to here you have 2 time delay, and here is a time delay. Okay, so at the end of the output, the signals happens 3 times the delay compared to the original change at the first input. And this have implications in the logic circuits when you have many different stages of logic circuits or many different levels. So I'll put down here what is the big deal if there's delay. So it just happens sometimes later. But consider these circuits here. So we have an input, A, go through an inverter, and then feed it through our NAND gate. So based on our truth table, so if A is 0, A bar is 1, and the 2, A and A bar will always be 0. Yep. So whether it is 1, whether A is 0 or 1, our output will be always equals to 0. And if this is a NAND gate, then the output will be always equals to 1. So my out2, regardless what the input, the output should be always equals to 1, based on our understanding of Boolean expressions and all the Boolean law. So if we have the input signals that change from 0 to 1, our output 1, which is going through an inverter, this is going to happen sometimes later. We got a delay. So we have a time delay here. And the signals came out slightly later at output 1, which is A bar. Okay, so signals go from originally 1 and then change to 0. And then this input 1 also fit into the NAND gate. So you can see that now this signals, output 1 and the inputs are not in sync. Therefore, we end up with a short time where the output go to low. And this violates our Boolean expressions that these functions should be always equals to 1. So we expect this output to be always equals to 1. But because of time delay, we have created a small moment when the output go to 0, which shouldn't happen. And we classified this as our static hazards. Okay, so this is the behavior or unexpected behavior that occur in this particular circuit. Although it is a very small moment, this time talking in terms of nanoseconds, but it happens. In this circuit, maybe it's not detrimental. The effect probably, if you try to view it in an oscilloscope, you probably will miss it. But in a larger circuit, this sort of behavior can trigger chain reactions to a much larger combination circuit. So we want to avoid this unexpected behavior, and we want to build circuits to mitigate or to prevent this sort of behavior happening. So that is for signals going from 0 to 1. But if you have the signals going from 1 to 0, you can see that this hazard doesn't occur. So it's only occur at a certain combinations of input transitions. So it doesn't happen all the time. Same circuits, changing the input from 1 to 0, you can see that the output to stay on as 1. So this hazard does not occur for transition going from 1 to 0. So it's only occur when the input going from 0 to 1 due to the propagation delay. So how can we mitigate this problem? Okay, so to eliminate static hazards, so when we design our logic circuits, as we looked at earlier on, we always go from the truth table and then to care map, and then in the care map, we minimize the function by throwing loops. So in this particular one, if I put my functions into my care map, and then if I minimize my functions, I end up with this sum of products, x and with z, or with x bar and with y. So in this circuit here, if we build this circuit, you can see that if we have the inputs, let's say y and z equals to 1, so my y and z stay at high, and then we change x from 0 to 1 and 1 to 0. So we change the signals x. Look at what will happen to the output. Okay, so this is the truth table of our circuits just now, or Boolean functions. So we want z and y to be equals to 1. Okay, so this is, I put down the wrong combination. So we want y and z to be equals to 1. So we want this column, sorry, this row. And this is the row. Y and z are equals to 1. And then x, we want to change them. Okay, so we change x from 0 to 1 or 1 to 0. This is the scenario. So x change from 0 to 1, and then y stay at 1, z stay at 1, and we expect the output to be always equals to 1. Okay, so the output, regardless what happens x, the output should be 1. So you can see that when we change x, this is our Boolean functions. So x going from 0 to 1. So our x and with z only happens a slight moment later. And then we invert x. So again, x, if we invert it, it only happens a slight moment later. And then we end this inverted x with y. So we end this with this. And therefore, it also just only happens a short moments later. Okay, so inverted by x, and then end it with y on the top. So 1, 1 gives us 1. And when this change to low, 1, 0 to give us 0, but it only becomes 0 a short moment later. And then we OR this function with this function. Okay, so we're looking at this graph here. So we got 0, 1, OR gives us 1. This bit here still 0, 1, still give us 1. And here is 1, and here still 1, let's give us 1. And then this large bit here is 1, and here is 0, let's give us 1. And here is 1, here is 0, give us 1. But you can see here, now we have 0, and this bit here is 0. And we end up with 0, 0, give us 0. And this small moment, the signals turn to 0. Okay, so this is what we call our hazards. This is unexpected behavior based on our truth table. Our function f in this scenario, when z and y is equals to 1, then this should stay at 1. But instead, we end up with a small time when the signals go to low. Okay, so that a hazard due to propagation delay. If I go back to my circuit, you can see that these signals feed directly from the input. These signals had one delay. So these signals here have two delay. So we have TP here, and then to the next gate, this has 2 TP, and then this gate has 1 TP, and then we're combining with all these two signals that has different time delay, and the output here is what created the hazards that we see just now. So we know that there's a hazard. So how can we mitigate this or eliminate these hazards? So going back to our care map, when we minimize the functions, we draw a loop of pair of 1 here and here on the top. And you can see that between the two loops are not linked. Okay, we have what we call open connections between the two loops. So the two loops is next to each other, but they are not connected. And this is what causes these hazards. So to eliminate these hazards, we need to link the two loops by drawing another loop here to introduce another product. So if you draw another loop, so this is not the most minimized function. So we have a redundancy logic here that we introduce by drawing this loop. But with that, we can eliminate these hazards. Okay, so you can see that the additional products that we introduce by drawing that loop will be y and with z. And our z and y is equals to 1 at all the time. And therefore, this also equals to 1 all the time. Therefore, even this hazards here occur due to the first two products and ended with this additional term, and that will correct the hazards in the output function f. Okay, so that is how you can eliminate these static hazards. So whenever you have, when you minimize your functions, when you draw all your loops, and if you end up with two loops that are next to each other but not connected, then you want to draw an additional loop to link them. So this is 3 variable. So in 4 variable, let's say I have something like this. So I can draw a loop like that, and then I have a loop like that. And I can see that in this case here, we also have one loop of 4 and one loop of 2. They are not connected. And this scenario will also introduce static hazards. And therefore, to eliminate them, we want to introduce an additional redundancy to eliminate our static hazards. So in ideal situations, so in all our ideal circuits, this will not happen. But when we have, in practice, we have propagation delay, and therefore not all the outputs actually fit into the input of a particular logic circuit are all in sync, and therefore this static hazard will sometimes happen if you minimize the function without taking into consideration of that static hazard. Okay, so this is just a diagram to stress that all my discussion here, we assume the pulse to be ideal, but in practice, this is how the pulse looks like when you transition it from 0 to 1 or 1 to 0. And there is a certain time delay for the pulse to react. And if you want to add this back to my previous discussion here, all you need to do is just to make all these pulse transitions with a delay, and all the argument is still the same, but you just look a bit more messy. So it's important that you know how to eliminate static hazards in design, and also know when the hazards actually occur. The next one is noise margin. So we have been talking about digital electronics, but I'm not sure whether you have actually think about why we want to use digital instead of analog. So here I put down that better noise immunity. Let's look at what I mean by that. So digital signals is a pulse-like signals that's going from one state to another state. So here we have 0.5 volt. We can assume that to be a logic 0 or low, and 4.5 volt we assume to be high or logic 1. Okay, let's look at sending signals through a device or channels for both analog and digital. Okay, so meaning that if I have a device, whatever this device is, it could be a logic gate or it could be a communication channels. So if I put an analog signals in here compared to putting the digital signals in here, and what I expect at the output, if my system has some noise. So in analog signal, the signals changes continuously with time. So if we put it through our device, will have some noise or interference that will affect this signal. So assume that my device introduces a noise with a random voltage of plus minus 0.2 watt. So if I put in 3 watt, I end up with output which is 3 plus minus 0.2. So if I put in this time varying signals, I'll end up with this time varying signals with an envelope. Well, my time varying signals will be this envelope, and the signals will change plus minus 0.2 around this value here. Okay, so if we know, just for argument's sake, if we know for conclusively that the noise is 0.2 watt, when it come up from the device, then we end up with either 3.4 or if we receive 3.2, because it's plus minus 0.2, we do not know whether the original signals is 3.4 or is it 3. Okay, so we're not able to predict what actually has been sent or what actually has been input to our device. Okay, so if we receive 3.2 watt, if we try to predict what the original signals is, if we know that the noise is 0.2, the likelihood of the input can be 3.4 or 3, and we have no way of telling. And that is with analog signals. And furthermore, in real signals, the noise is random. So we do not know what this noise is. Could be anything between plus 2 to minus 2, let's say. In digital signals, so we have low is 0.5, high is 4.5. Let's say that's what we define our logic, 1 and 0. Putting through the same device, introduce the same noise. So if we transmit a logic 0, this is 0.5 watt, we receive 0.5 plus minus 0.2. And if we put in this rectangular pulse, we end up with signals that look something like this. So the low will vary between 0.5 plus minus 2, so going from 0.7 to 0.3. And then here you go from 4.7 to 4.3. Okay, so here it's between 4.7, 4.3, and here is between 0.7, 0.3. But because it's digital, our input can only be 0.5 or 4.5. So if we receive 0.7 or if we output a 0.7, we know that the original signals is 0.5, and we can correct it back to 0.5 because that is what has been sent. Or if you receive 4.7, we can correct this to 4.5 because we know that there is 4.5 has been sent. So, which means that whatever noise that is introduced can be removed from the output signals if it doesn't, if the noise is not big enough to change the signals from low to high, and the noise can be removed or the signals can be corrected to what has been set. So having said that, so we need to be able to decide at what level the signals to be a logic 1 and what level the signals can still be called logic 0. So one way of doing that is to put decision line. Anything above this line, call it a logic 1. Anything below this line, call it a logic 0. So we introduce some form of threshold to decide what constitutes to a logic 1 and what constitutes to a logic 0. And in this case here, anything in between is undetermined. So which means that if we receive a signals in this range, then it's undetermined. We do not know whether is it a logic 0 or is it a logic 1. So why do we do that instead of putting the decision line spot on right on the middle? Okay, so if we make right at the middle, so what happens if spot on at 2.5? Is there a logic 1 or is there a logic 0? Or if you have noise sitting around this value, so if it's fluctuating between 2.5 and the signal's going high, low, high, low, high, low. In that scenario, if we make the middle line as the threshold. So we don't do the middle line as the decisions, so we put a level slightly below to be a logic 0 and slightly above to be a logic 1, and we define a zone which we call a forbidden zone, which means that if signals fall within this voltage level, then we can define that as to be an error signal. Okay, so in this diagram, on one side, I show the transmit or output. On the other side is receive or input. Okay, so you can think of this as a logic gate. This will be my output. And this output will be fed into another gate. And this will be my input. Okay, so the output will be a signal to an input of the next gate. So here I put down what is the problem with this. So if you define a voltage high here, they're the same from the output to the input, and the voltage low the same for the output to the input. So the problems is when we connect an output to an input. So in this line here, the voltage can drift. So sometimes you have losses in the wiring. So let's say I have, say, 3 watts here. So the output a 3 watt, and then when this 3 watt fits into the input of the next gate, then the voltage can drift across the wire, maybe end up with 2.8 watts at this point here. Okay, so if we define this to be, let's say, 2.9 watts, so when it comes out from here, it is still a good logic high. But when you feed it to the next gate, it has fallen into a forbidden zone. And therefore, this signals here no longer a logic 1. So we need a better model. So instead of having the output and the inputs to have the same level, we define the output slightly stricter. Okay, so the output has a smaller regions to define to be a logic 1 and a logic 0, and then the input has a higher region or higher range for it to be a logic 1 and logic 0. And we defined the output logic high limits as VOH and the logic low limits as VOL. So O is for output, and L, I'm sure you work it out, that is low, and H is high. And then on the other end, at the input, we have VIL, which is the input, low, and input high. So in this scenario, we allow the signals to drift slightly from the output of one device going to the input of the next. And this difference between the level from the outputs to the inputs is what we call a noise margin. Okay, so when we have, like what I've done just now, let's say output from my inverter and then going into my NOT gate, let's say. So I have the output from here. You allow some noise added by the line before it go into the input of the next gate. Okay, and that noise allowed is called a noise margin. So as long as the noise introduced by the interconnections is not larger than the noise margin, then we have less likelihood of causing an error in the circuit. Okay, so the two noise margin, one is the margin for high, and the other one for the margin of low, can be worked out by taking the difference between the two levels. Okay, so that is on noise margins and other things that you need to think about when you design practical logic circuits. So because of noise in interconnections can also affect the logic. So when you have a certain level of logic coming from the output, the interconnections can introduce some noise. And if that noise is very high, then you end up with a different logic going into the next gate. I believe this is something that you see in the lab as well. Some of you very often not able to get the end results of your experiment. Sometimes it's because of the connections between gates. For example, you test it on the pin coming out from the NOT gate, and if you test it on the pin coming into the NOR gate, for example, it will out to be of a different logic. And that is because there is a problem in the interconnections between the two. Could be a high resistance on the breadboard that you use that degraded the voltage level from the outputs to the input. The next one is called fan out. This is also a practical considerations when you design logic circuits. So fan out, in simple terms, is the number of gates inputs can be connected to a single driving gate output without overloading the driving gate. What it means, so if I have one gate, my output of this gate, you probably use this output as the input for a number of gates. So you need to know in this output, how many gates can you actually connect to? Okay. So you can't connect to infinite number of gates because it doesn't have enough current to drive the gate. So for example, if this goes to a logic high, it has a certain current, and in this gate, for it to be logic high, you need to maintain a certain current. So if the current from the output of this not enough to drive all the number of gates you connect to it, then you will not end up with the logic level that you're expecting. So I'll put down here, the total current driving the inputs of the gate must be smaller or equals to the current driving from the outputs of the gate for both states, which means that for both high and low. So in other words, the output gate current has to be equal or higher than all the input that you try to drive. If you drive more than that input's current, then you're overloading this output gate. And that leads to a simple calculations to calculate how many gates you can actually connect to a particular output of a gate. So in datasheet, you list down the current, IOL, so this is the current, I is the current, O is output, L is low, H is high, and then you have the current IL, and this is the input. Okay, so data sheets will list down what are these parameters, and with these parameters, you can do a simple calculation to work out what is the safe number of gates inputs can be connected to the outputs or one output of the gate. Okay, so this is also another important thing, so that you don't connect too many gate inputs to a particular output of the gate. If you do, if you exceed this value, then you have a likelihood to end up with a logic that you're not expecting or creating an error in your overall circuits. And then I put down here as a side note, there's also a term called fan-in. And fan-in is actually referred to the input current to a single gate. So this current here is called fan-in. Okay, so these are some of the practical aspect or practical consideration you need to consider when you building logic circuits.